In this video, we're going to go through a complex unfamiliar question involving critical path analysis. So we've got a company needs to complete the following project as quickly as possible. Each task can be completed by a single employee and must be completed before that employee can start the next task. We've got a precedence table here, and the owner believes that this project can be completed in minimal time with only 3 employees. We've got to evaluate the reasonableness of this belief. So first things first, I've drawn an activity network. Now, because I want to get more into the complex unfamiliar part of this question, I'm not going to go through how I drew that network. I've got another video where I talk about forward scanning and backward scanning. I'll put a link to that in the description of this video. So we've done the network, we've worked out the minimum completion time is 14 days. So like I said before, the owner believes that this project can be completed in minimal time with only 3 employees. So we're basically checking if we just had 3 employees, if it would be possible to complete all of these tasks in 14 days. So the best way to do this is to make a bit of a table like this in red here. So notice I've got employee 1, employee 2, employee 3 here because we've got 3 employees. We're checking if we only have 3 employees, can they still complete this project in the 14 days? Up here we've got the days labeled from 1 to 14, and each day we're going to assign an activity to an employee. So some ideas. Worker 1 can just do all the critical jobs, right? Someone has to do all the critical jobs to complete this whole thing on time anyway. So worker 1 is going to do all of those jobs there along the blue, which is the critical path in this case. So notice I've started to put values into employee 1's box. So on day 1, 2, and 3, he'll do activity A. On day 4 and 5, he'll do activity C, which is straight after activity A, etc. Then he'll go on to do E, H, and J. Now, another idea for employee 2 or worker 2. So worker 2 can do non-critical jobs, and because there's no reason he can't start straight away, he can start on day 1 by doing activity B. So I've just added that into this table here. Now, another idea, right? So worker 3 or employee 3 can start with activity G and activity I when worker 2 starts F, right? So the third employee doesn't really come into this picture until day 5 because he's got to wait until the second employee has finished activity B, which takes 4 days. So worker 2 or employee 2 is going to do activity F, and during that time, employee 3 is going to do G and I. So I've added that to this table here. Now, let's just check how many jobs have been completed at this point and if we've missed any jobs. So I've just gone and ticked all of these in purple, and we can see that activity D still needs to be done. So the only leftover job is activity D, and that takes 8 days. Now, if we look at employee 2 and employee 3, employee 2's only got 6 days there, but the job for D takes 8 days. So there's no possible way employee 2 can do it and get it finished in time. And same with employee 3, he's got even less time. He's got 1 less day. So with these 3 employees, there is no possible way for them to finish this project. Assuming we did have a 4th employee, that 4th employee could begin doing activity D straight after employee 1 has finished activity C, right? Because it was activity C and then straight after that was activity D. So if we did have a 4th employee, he could start doing activity D. It'd take him 8 days to complete it, which would mean that the task would be completed within 14 days. However, as we've just proven, if there are only 3 employees, there's no possible way for them to complete this project in 14 days. Therefore, meaning that the belief is not reasonable.